Okay. Since this conference is a mixture of string theory and experiment, so I decided to talk about topics which are hopefully relate the two up in some way. So instead of go step by step, I would like to summarize the basic point I want to make. That is, when we talk about cosmic superstrings, we're talking about strings in string theory. They have properties very different in some ways than the cosmic strings people have been talking about in the 1980s and maybe early 90s. And the properties that endowed on the superstrings surprisingly tend to enhance the probability of detection. And that's the main message I want to go over with you. And since we don't know much about string theories in terms of how we describe nature, I think that gravitational wave burst detection of string theory superstrings will be a really good signature or evidence for string theory, which is clearly very lacking at this moment. So the conclusion I have is that there's a good chance that LIGO, the Virgo and Cagra, can detect some of them. And of course, if we go to LISA, then the chances would be even better. So some of the work we did, I did this with David Chernoff, but the work that I would describe here mostly will be in a paper to appear. So this is the summary, what I want to pass the message to you in case you miss most of the rest of the talk. So in 1970s and early 1980s, it was proposed by Kibble and others that cosmic strings as topological defects coming from spontaneous symmetry breaking can be produced in early universe, and they will evolve forming a scaling network independent of the initial production mechanism. That's very important. This is in contrast to zero-point objects, monopoles, or domain walls of membranes. So strings have very special property such that it will go to a scaling network. And I'll describe this in a moment. And what they do is that the motion evolution of the strings will generate density perturbation, and the density perturbation can be the seed for structure formation if the string tension mu, and we always multiply by Newton's constant to get a dimensionless quantity, is roughly 10 to the minus 6. For this reason, cosmic string have received a lot of attention, a lot of work being done in the 80s and so, because it provides an alternative to inflation. Now, by early 1990s, Kobe data came out and slightly disfavored cosmic strings, but it's not clear. By the late 1990s, with Boomerang, Maxima, and Darcy, which sees the acoustic peaks in the power spectrum, then the inflation is clearly supported, and cosmic strings are ruled out, because the fluctuation produced by cosmic strings are active, and they don't have acoustic peak. They have a smooth power spectrum. So that's clearly ruled out as a source of density perturbation for structure formation. Now, let me briefly go over this. We know that the radiation density goes like 1 over 8 to the 4th, and matter, non-relativistic matter goes like 1 over 8 cubed. And strings, because it's one-dimensional object, goes like roughly like 1 over 8 squared. So if you have any strings, expansion universe will make this much more prominent than the other two. So even though initial production is very small,